All right. So today we are starting a new unit. We are learning about chemical reactions. I'm not going to lie and say that this will be an easy unit, especially if you don't love math, but we're all capable. So we're all going to be able to identify the five types of reactions by analyzing the structure of chemical reactions by the end of the day. So our essential question is just what are the different types of reactions? Okay? Because that is our goal, just to be able to look at a formula and say, oh, it's this type of reaction. And this is how we're going to do that. So before we even get started talking about what a chemical reaction is, let's go all the way back to the beginning of our learning and remind ourselves of what physical changes are and what chemical changes are. So, physical changes we know are just changes in physical state. Chemical changes are changes in chemical composition. Okay? So, if I'm looking at this picture here of a glass shattering, is this a physical change or a chemical change? Great. So, this is a physical change because it's still a glass, it's just in a different form now. What about now? This can of crush being crushed. Also physical. Great job. What we see here is what appears to be a pile of ashes erupting into a different form because of fire applied. What will we say this is? Okay, great. So we would say that this is an example of a chemical change because you've created something completely new from something not that, right? What about here? It looks really gross, but that is a chemical change, correct? Because you have what is essentially a new substance forming from this combination, this mixture. And here, so it might be a bit tricky. Okay, so I heard some people say chemical change, but I would disagree just a little bit. It's confusing, but this would be considered a physical change because all that's happening here is water is instantly becoming ice. Okay, so it's still a physical change. It's still water. It's just in a different state. What about with this? Physical or chemical change? Again, perfect because it's still water. It's just in a different state. It melted when the ball was applied to it. Great job. So, just a quick reminder that in a chemical change, we see a change in the makeup or the composition of the substance. In a physical change, there's a difference in the appearance, size, or display of the substance without a change in the composition or the makeup. So, some indicators that we have a physical change is that the substance isn't changed, just the size or the shape. So, that's like me taking this sheet of paper and tearing it in half, right? It's still a sheet of paper. I can put it back together. I can glue it. I can tape it. I can staple it, whatever, but it's no longer in the original shape. A change of state. So, that's like water becoming ice, becoming gas, something dissolving, something bending, crushing, mixing, cutting, etc. And then your chemical changes cannot be reversed. They produce heat, sound, light, or odor, a smell, and sometimes foaming or fizzing, like Alka Seltzer being added to water. Great. So now that we've reminded ourselves of the difference between a physical and a chemical change, let's talk about what we call a chemical change. So chemical changes are just reactions. And scientists use chemical reactions to describe the chemical changes. They write those reactions as formulas with what we call reactants on the left-hand side and products on the right-hand side. So our reactants are the starting substances, the things that make everything happen. Those are what we would call our ingredients. And then on the right-hand side of the arrow, which is like our equal sign in a traditional math problem, we have products. And products are just the substances that are produced after the reaction happens. So let's think about this like baking, which is something that we all have seen done at least. When you are making a cake, you have lots of ingredients. You have eggs and milk and flour and maybe some vanilla and some sugar and baking soda. All of these various things that you mix together in bowls and you place into the oven. So those are your ingredients. And then what comes out of the oven is the product, aka the cake, right? I can't take that cake back into its previous form. It's always going to be a cake now. So the ingredients are what I started with. The oven is the arrow. That's the equal sign. And then the products are the cake in its final form. And that's what we're looking for when we're talking about ways to identify chemical changes or reactants or reactions. I'm sorry. Okay, so can anybody tell me, based off of what we learned just now, what are the reactants and what are the reactants and what are the products in this particular formula? Let's start with where the reactants are. Okay. Okay, so the reactants are on the left. Great. And what about what's happening on the right? We call those the products. Perfect. And that is something that we need to always remember when we're looking at chemical reactions. It doesn't matter what elements we're working with. In this equation, we have zinc and silver nitrate, which becomes zinc nitrate and silver. It doesn't matter which elements we're working with. What matters is that we understand that the reactants are always on the left and the products are always on the right. So again, what are the reactants here and what are the products? Mm-hmm. Great. So your carbon hydroxide over here and your oxygen, those are your reactants. And then your carbon dioxide and your water on the right hand side are your products, always. Okay, so now that we've understood what's on either side of the arrow, we are going to talk about the 5 different types of reactions. Our first reaction is synthesis. And all synthesis is when 2 or more reactants come together to form one product. What we call the general equation, aka what this looks like, is usually element 1 plus element 2 becomes element AB, or element A plus element B becomes element AB. An actual example of how this would look in a formula is that we have 2 units of copper, or 2 atoms of copper, and 2 atoms of oxygen, and they combine to form what we call cupric oxide, which is that greenish blue tint that you see on your pennies as they age or if they've been exposed to too much water. It's also what happens to the Statue of Liberty and why she looks like she does now. One of our real life examples down here in gift form, we have Beyonce and we have Jay-Z. They're great individuals. They're showstoppers. They make great music, right? They're power individuals by themselves. And then they synthesize and they become one, aka they got married, they've created a family. Okay? So Beyonce is A, Jay-Z is B. Together, they form AB. Our next type of reaction is decomposition. And decomp is the exact opposite of synthesis. One reactant breaks apart to form two or more products. So the general equation, which again is just what this looks like, is AB, element AB, breaks apart into element A plus element B. An example of this is what we see here. Hydrogen, is this carbonate? Hydrogen carbonate turns into water and carbon dioxide. So what was once one has split up into two separate compounds. Our real life example is Kylie and Tyga. As we know, they were a couple, they have a baby together, they were a thing for a little bit. And now, in our example, they have broken up and they are their individual selves once more, no longer a couple. Now they are just Kylie and Tyga by themselves. Okay? Yes, I know. I've heard the rumors that they might be like getting back together, but it's not the point of this lesson. Okay, so what is the relationship then between synthesis and decomposition reactions? What do they have in common? What's different? Uh-huh. Great, good. Okay, so what we have, the relationship between synthesis and decomp reactions, is that you have two elements that either split up to become individuals or join together to become a couple. Okay, that's what we're looking at typically in these examples. Our next two types of reactants or reactions share a similar name, and they are very similar in form, but they're not exactly the same. The difference is small though, so we have to be paying attention. The first type of reaction is what we call single replacement. And that just means that one element replaces another one in a compound. And so one element winds up single by itself. So the general equation looks like element A plus element BC becomes element AC plus B. A real life example of this is what happens when cars begin to rust. For example, you have iron, which is the metal, and then water joins the party, and then hydrogen leaves the party and creates ferric oxide over here, ferric oxide, which is the rust that you see. Okay? So our real life example is Drake. He's single, he's living it up, he's cruising Instagram. He sees a great picture of Rihanna. He says, wow, I gotta have that. But Rihanna, she's hanging out with Chris. They're happy, they're lovey-dovey, right? So what is Drake gonna do? Drake is gonna scam his way into this relationship. And now the product of that scamming is that Chris is alone by himself. He's confused as heck. Like, what just happened? And Rihanna and Drake are all booed up at award ceremonies living their best life. Okay? So Drake stepped in and replaced Chris. He threw him out of the situation. Now Chris is single and Drake has a happy home with Rihanna. So in this example, Drake is A, Rihanna and Chris are BC. And then on the product side, Chris is B and Rihanna and Drake are AC. Okay? Our next example is double replacement. What that means is that the ions in an element simply trade partners, and a precipitate, which is a solid that forms inside of a liquid, forms. Okay? So the general equation is element AB plus element CD becomes element AD plus element CB. I guess a better way of saying this would be compound AB plus compound CD. Same thing. Okay? Your real life example is calcium chloride plus silver nitrite becomes calcium nitrite plus silver chloride. Okay? It looks like this. And then in our pictorial form, We have Selena Gomez and the Joe Bro. I can never remember their names. I think this is Jonas. Wow. All their last names are Jonas. I think this is Nick, is what I meant, but I'm probably wrong. I know it's not Kevin because Kevin's the oldest one. We have Selena and we have her Joe Bro. And then Miley and Justin Bieber are doing their thing. They're happy. They're living on the street, right? They're going somewhere cool, probably going out to eat. Can't do that anymore. It's tragic. And then the next thing you know, the Joe Bro is now dating Miley and Justin is dating Selena. Okay? So the partners, the male partners for our lady friends down here, they just switched it up. Okay? That's the same thing that's happening in a double replacement reaction. Important to note is that in double replacement, the elements that are going to move or the ions that are going to move are always the ones in the back of the element of the compound. So here we have calcium chloride. Chloride is going to swap places with nitrite, the NO. Silver and calcium are going to stay exactly where they are. They're not going to move. Okay? So it's really important to know that what's changing in a double replacement reaction is what's at the back, never what's at the front. So again, what is the difference between double replacement and single replacement? And here are two examples of single and double replacement. Looking at these equations, what do you think is the difference here? Perfect. So the differences between double and single replacement are really simple. It's just that in single replacement, only one element is swapping sides, and in double replacement, two elements switch with each other. Okay? And our last type of chemical reaction is combustion. And combustion is when a hydrocarbon, which is just something that can catch fire, reacts with oxygen and it produces steam, otherwise known as carbon dioxide, and water. So the general equation is a hydrocarbon, which is CH of some form, plus oxygen turning into carbon dioxide plus H2O. An example of this is CH, which is your hydrocarbon, plus oxygen, becoming carbon dioxide and water. And our pictorial description has a piece of wood, a trunk, catching on fire and producing water and carbon dioxide, aka a steam. Okay? The combustion reactions are the easiest to figure out, guys, because they are always going to produce carbon dioxide and water. So if you look at the end of a formula and you see, oh, CO2 and H2O together, that's combustion. So these are the easiest to just identify very quickly. Now we're going to go ahead and get some practice in, okay? Have a great time trying these equations out, and then we will work through them or talk through them the next time we meet up. Bye.